Derivative is all about slope, and it's that slope as it changes. So we're going to be looking at a few different graphs here, and we're going to be kind of comparing and contrasting them and looking at what's going on. You'll notice that the first graph has distance versus time. So the red line is how my distance is changing with time. That is also related to velocity. Velocity is the change in distance over the change in time. And if I were to write that out, the change in the distance over the change in time, another way I could have written this is the change in the y values over the change in the x values. Another way I could have interpreted this is slope. Velocity then is just the slope of your distance time graph. If I looked at these three lines and I were to ask you which one had the fastest speed, you might look at the very beginning times and say that the red line had the fastest speed. As I moved on out further in time, this blue line is really going fast, because if I look at the slope of this line right around in here, I'd say, wow, it is really climbing, and the velocity of the blue line is changing with time. It is getting faster and faster. If I look at the green line, I see that the green line is not going nearly as fast as the red line, especially on this front end. And then this flat part here tells me that the whatever it is, whoever it is that's doing this is actually not moving at all, because their distance doesn't change with time. The velocity here would be 0 because the change in y over the change in x would be 0. So let's try to draw, if you will, what this velocity would look like. So if I look at the red line, I see that the speed doesn't change with time. It has a constant speed. In other words, it has a constant slope. So whatever that slope might be, we'll just say that it's on up there, around here. And there might be what the velocity of the red line would be. Let's look at the velocity then of our green line. Not quite as fast as the red line, so I'm just going to draw it somewhere down here, all the way up to this particular time, and I tried to draw a horizontal line there. Then the velocity or the speed drops off to 0 here, whatever time that is. And what kind of slope is this? This would be a negative slope, and it's steeper than the other, so I'm going to say it has a greater derivative there, or you might say it was even less than because it was negative. I just want that value to be higher. I'm going to look at the blue line, and the blue line is changing with time. It is getting faster and faster, so it might be a curve, it might be a straight line. I'm just going to draw something like this because I'm seeing that it is getting faster and faster with time. If we understand the concepts of the derivative and just the fact that it is slope, then we can draw our derivative graphs, or have some good idea of what our derivative graphs look like just from looking at pictures, and understanding that the derivative is nothing more than slope will help you tremendously in the solving of all of the different problems from here on out. So it's extremely important that you understand that derivative is slope, but it's the slope at any point along the curve. So the derivative, or the slope, at this particular point is different than the derivative at this particular point. I have for you here a graph of a ball toss, and there's my formula that I plotted right there. And I have thrown a ball off a cliff, chunk, and there would be the graph of that. The first question is average velocity. What we're looking at here is the difference between a secant line and a tangent line. An average velocity, we're talking about the slope from time 2 and time 0. So time 2 and time 0, that would be this slope right here. I need those y values if I were to get that slope. That's what this top part is about. I need that y value at 2. That y value at 2 is actually 0 minus the y value at time 0 would be 64 over 2. The average velocity is negative 32, and I believe this is in feet per second. Yep. If I were to look at the average velocity from this same 0 point to point 6, that would be from here to here, I would take the value 58.24 minus at 0, it is 64, and then 0.6, and crunching those numbers on my calculator gives me negative 9.6 feet per second. All right. This average velocity is computed using what we call a secant line. A secant line is just a line that goes through the function in 2 points. For instantaneous velocity, we're looking more at something called a limit. That's the whole reason why we did limits. I would like to know what the speed is, say not just average, but I want to know exactly at this point to point. I want to know exactly what it is right there. How I would go about doing this is just picking 2 points and getting those 2 points closer and closer together, which is why we did chapter 2. Because a derivative is getting those 2 points as close as possible but without touching. So that will get us what's called instantaneous velocity. We look at instantaneous velocity every day that we drive our car. If we look at our speedometer, that gives us instantaneous velocity. Getting these values, I need the y value at 0.21, 63.294, minus the y value at 0.2, 63.36. And then this value down here is 0.01, and then I'll crunch those numbers. I get negative 6.6 feet per second, and let me see if that makes sense. And I know that's pretty close to what that actual value is, because I'm pretty close to 0.2 seconds, because I'm just right in there. Notice that the steepness of the line decreases as I'm up here at the top. When I first throw the ball off the cliff, and then my ball gets faster and faster, or the slope of these tangent lines, or the slope of the derivative, makes it so the ball is moving faster and faster. So let me do my next one really quickly, just getting closer to that value of 0.201. Now I tried to get my calculator to do this, but because the calculator only carries out to 3 digits, it gave me an erroneous answer. So it was, in other words, it was garbage, because of the fact that our calculator truncates numbers, and I needed more precision I needed more decimal places in order to get an accurate answer here. So I'll write these in. Plugging in the values and just crunching them, I get closer to the actual value of the instantaneous velocity at 0.2 seconds. Let's look at this definition of the derivative. If you'll notice, we have f prime of t, that's how that's pronounced. We can also write it as f prime. We will say f prime of t, we can say the derivative of f, any one of those means the same thing. This part right here is the slope, the difference in the y's over the difference in the x's. And this part just says that those 2 points are getting so close together such that they're so close together that their difference is going to 0. That's what that is saying. And this is our definition of the derivative. We want those 2 points on our graph to be so close that it's just at 0. Let's see how we would plug this in. I need this f of t plus delta t. So s of t plus delta t. That's usually the hardest part for students. We went over function composition in chapter 1. And what we did was we said 64 minus 16 times whatever that we're wanting to put in there inside of our function. And in this case, we want inside there for t, we want t plus delta t, because that's what we were given to put inside there. If you'll notice, I went ahead and wrote this out for clarity reasons, really. And that is what this guy right here is all about. That is that f of t plus delta t part. This guy is just the f of t, or the s of t in our case. Now I do all the algebra. So let's watch me do the algebra of this, because it's extremely messy and you'll have to keep track of a lot of junkola. So I'll have 64 minus 16 times, and I'm going to do that multiplication, that t plus delta t, and I'm just going to, as you guys call it, FOIL it out. So I want t plus delta t times t plus delta t. That'll give me t squared plus 2 of those delta t's, and know that delta t and t are not the same thing, plus delta t squared. Minus, I'm going to go ahead and distribute that, minus 64 plus 16t squared all over delta t. Still playing. The limit as delta t goes to 0 of 64 minus 16t squared minus 32 delta t minus 16 delta t squared minus 64 plus 16t squared. This is gross over delta t. I have some things that'll cancel. I got a 64 here and a minus 64 there. I got a plus 16t squared and I got a minus 16t squared there. Look for things to cancel, because they do when you're working this derivative definition. Writing down what I got left, negative 32 delta t squared minus 16 delta, oh, you weren't that, you were delta t and then a t, sorry, you're delta t squared, all over delta t. I see that I have a delta t in each one of these, so I'm going to pull it. The limit is delta t goes to 0 of delta t, pulling that out. I'll go ahead and pull out a negative 2. And no, all right, I'll go ahead and do it. I said I would. Then I've got 32t minus 16. That'll be a plus because I pulled out the negative, delta t all over delta t. Delta t's cancel. Then I can plug in a delta t equals 0 because it's going there, and if I plug in a 0 for this guy right here, this term drops, leaving me with negative 32t. And that is your equation for the slope at any point along the curve. That is the equation of the derivative. Equation of derivative for this function, or slope. So it's the equation for the slope at any point along the curve. So if I want the instantaneous slope at point 2, I will just plug in negative 32 times that time I wanted point 2, and if I crunch these numbers, I get it is identically negative 6.4 feet per second. Now, if I go back to my graph and I find that this is negative 6.4 feet per second, and I look at what was happening as that point got closer and closer to point 2. When I was point 1 away, I said that the instantaneous slope was about negative 6.6. When I was a thousandth away, I said that it was negative 6.41 feet per second. See how it was getting closer and closer to the actual value. So this will get me close. If I choose the points close enough, this gives me the exact value of that velocity or of that slope at that point. The next thing we're going to do is look at finding the derivatives just by looking at the graph. The textbook has you do this in several of the different homeworks all along in every section basically. So you want to see if you can do this. If the red is our original function, I'm going to draw down here the derivative. So this will be our, in red will be our, okay. So our original functions we'll put in red and we'll put our derivatives in blue. What is the slope doing here? I'm looking at how the slope is changing over time. I see that it is a positive slope. So up until this point it'll be a positive value. I don't know what that value is. I just know that it's constant. It's not changing. What is the slope doing here? Well, the slope here is 0. It is not changing at all. So the derivative graph would look as such. Next graph, what is the slope doing here? It is decreasing, it is going down, so I'll have a negative slope. Just put it right here until I get to that point. I go to this next one. It has the same value of slope as the one that was going down, but this time it's positive, so I'll try and draw it at the same height there. And it is straight across because it's not changing. Once again, the slope goes straight across all the way to here. Whoops. Straight down. All right, I am now determining or drawing the graph of the derivative without even knowing what the function is, just looking at the graph, because I'm going to carry on all the way for that one. All right. And then I would go back up and then over. Nice. The next one, what is the slope doing? The slope is, if I were to kind of look at this, what the slope is doing here at the tangent lines, the tangent line, and what is the slope doing here? Well, right here I know that the slope is 0. I got that point. But here, the slope is negative, and it is really steep and then getting less steep as it goes down. I'm going to draw something like this. Whatever it is I do on the left hand side, because it's symmetric, that line needs to be the same over on the right hand side. Alright, next one. Looking at slope once again, just trying to figure out what the slope is doing. See that the slope really isn't that much here. It's a positive slope, but it's not a lot. And then right here, it increases quite a bit. And it increases and then it levels back off. So let's see what we think that might be doing. So it increases quite a bit. So I would say that it's almost 0 here. Then it increases quite a bit, and it's symmetric, and then the slope tries to go towards 0 once again. Let's look at what this function is doing. I like to pick out my 0, so I'm going to do that. I've got a 0 here, a 0 here. Notice how the slope of the tangent line at all of these places would be 0. So I'm just going to go straight down and mark some zeros because I know these zeros are happening. Okay. What's going on now? On this side, it's a positive slope, but the slope, notice how the slope is decreasing. So it's positive, so it's up here on the positive part of the y's, but it's decreasing. The value is getting less. All right. Now the slope turns and is negative, and the slope gets faster and faster, it increases, and then notice how the slope then decreases again. So I think it's going to do something like it's increasing then decreases again so that it can go through there. Then my slope is going to basically do the same thing again. It's going to get faster and faster, and then it's going to slow down. Then my slope is negative once again and makes the same shape as it did on this side. Notice how this looks like a sine wave and this looks like a cosine wave. Interesting. We'll investigate that more later on. Let me get my zeros here. This looks like the absolute value of a sine, doesn't it? Because this bump has just been flipped up. So my 0, I got one here, here, there, and there. I've already drawn this part. I know what that does. It's increasing and then gets slower, so it does the same kind of deal as this. Then what does this, after it hits this 0, then what does it do? Let's see, its slope is 0 there. It's negative slope. So I see this is a positive slope. That's a negative slope. So it has a negative slope, so it's kind of like down here. But then it does this weird thing, and I can't tell you what the derivative is doing there. That's going to be what we call a non-differentiable point. Positive slope once again. So from there it's positive, but it's decreasing and then becomes negative. Oh, bet this does some sort of weird kind of shape as such. What do you bet me? These non-differentiable points, the function is continuous there, but it does have non-differentiable points there. Which leads us to our last point of continuity and differentiability. This function that I looked at last is continuous, but it is not necessarily differentiable because of these corner points. We have a theorem that states that if f is differentiable at point A, then we know it's continuous. However, as you have just seen, just because it's continuous does not imply that it is differentiable. So we have these 3 points. When you're asked to determine whether or not a function is differentiable at A, if you see that it is not continuous, you can say it is not differentiable. If there's a corner, you can say it's not differentiable there. If it has a vertical tangent, you can also say that it's not differentiable there. So let's look at an example. In example 8, we're supposed to find the values of x over this entire realm where g is not continuous. So for the answer to A, let's begin for A where it is not continuous. I can say that at x equal -2 it's not continuous. and at x equal 2 it is not continuous, because I would have to pick up my pencil. There's a hole there at 2, so not continuous. The B part, not differentiable. It is not differentiable, of course, at -2 and 2 because it's not continuous, but it is also not differentiable at 0 because of that corner point. Sketch the graph of the derivative. All right. If I'm going to sketch the graph of the derivative, I see that it is a steady upward slope. I can actually determine, no, I can't determine that value, but it's steady and it's positive, so I'm going to draw something like this. This is a downhill slope. It's negative up to some sort of corner, and it's changing its slope as it goes faster and faster from there, and it is negative, so it's going to be somewhere down in here. Looks like it starts off at 0 and then does something like this. This one is a positive slope. It is very fast to begin with, so it comes from way up here, and it looks like it slows down until it hits this 0 point here. And then we don't have a derivative at this 0 point because it is not continuous, and it is negative. Looks like to me it's a negative slope, and it's getting fast and it's speeding up as it goes, something like that. So let's put our little hole on there to show that we have a hole there, and let's put a hole here, show that's there, and a hole here to show that it's not differentiable there. Let's look at the books. You might say that's a little prettier than mine, but you know, we got the exact same thing, didn't we? Lovely. If you have any question about this, see me at the Collaborate.